So when we see the applications of Gauss law, there are three important applications. The first one is applying this for an infinitely long charged wire. Okay. So if I observe this, then I have an infinitely long charged wire, right, on which there is obviously charge that is distributed uniformly. So what do you mean by uniform distribution? Listen, if suppose I take a wire like this, 1, 2, 3, 4, for instance, there are 4 point charges summing up to give you the total charge, and let's say the length of it is, for instance, 8 units. Then what will you write the value of lambda as? Lambda will be written as 4 units divided by 8 units. So the lambda value is going to be half. See, this is only for understanding purpose, right? Suppose I break it into 2 charges, right? If suppose I break it into 2, if I write 2 in the numerator, what should be in the denominator? I should have a 4 in the denominator so that I have the same half for the lambda. That is the meaning of uniform distribution of charge. Am I clear with this? Right. So you have a system of this format. So if I take a point P which is at a distance r from it, right? Now, first thing is we need to define the type of charge density. What is the type of charge density we can define here? Linear charge density. The first step says clearly lambda, right? Second step, it says we need to consider a Gaussian surface around this. So the Gaussian surface is supposed to be symmetric with respect to the charge distribution. Okay, listen to this carefully. If this point P is here, the point P can be here, it can be here, it can be here, it keeps on going like this, right? So when you join all these points, you get a straight line. Similarly, this point P could have been on the other side at the same distance r. That is another straight line, right? But at the same time, this point P could have been here. It could have been here in the space. It can be anywhere. So when you join all those points, then the shape that you are going to get is going to be a cylinder. So this is going to be the Gaussian surface, and we also ensured that the Gaussian surface is passing through the point where we are interested to calculate the field. Next step. On this Gaussian surface, we need to consider a small area dA. So if I take the area to be dA like this, see, for example, let's take this water bottle, assuming it to be cylindrical, okay? If I take this to be dA, then this dA is over here. Then for this dA, right, for this dA that I have considered, what is the direction of what is the direction of aerial vector? This is the direction. It's radially outward. So I have taken this dA in this direction, right? So consider dA and take the direction. What is the fourth step? Direction of electric field. Since here we have a system of positive charges, due to the positive charge, what is going to be the direction of electric field? Is it away or away? So it is going to be away, again perpendicular to this. So this is going to be the direction of electric field also, right? What is the next step? Find the total charge that is present. So if I take this height to be h for the time being, right? So what is the charge density? So charge density is lambda, but we know that charge density is the charge per unit length. So what is the total charge enclosed within this Gaussian surface? See, lambda is equal to q divided by L. So q will be equal to lambda into L, right? So in this case, what will happen is the total charge inside the Gaussian surface is equal to how much? The linear charge density multiplied with the length of it, which is h. Am I clear with this? What is the next step? Apply Gauss law. the surface integral of E dot dA in the vector forms is equal to 1 by epsilon naught times the charge enclosed by the Gaussian surface. So I'll write this formula every time. What is the angle between electric field and dA? 0. So I can write it as E into dA. So in this case also electric field is a constant. So I can take the electric field outside. So E into the surface integral of dA is equal to, what is the charge enclosed within the Gaussian surface? It is lambda into h divided by epsilon naught. Now tell me one thing. For this surface, if I add all the dAs that are present here, what do I get? What surface area? You get the curved surface area, because if you see for the cylinder, here also you can take a Gaussian surface. Sorry. Here also you can consider a small area, meaning you can take an area here. The area vector's direction is upward. What is the direction of electric field? Rightward. What is the angle between both? 90. So what is cos 90? Because when you're doing dot product between two perpendicular vectors is 0. Similarly, if I consider another dA at the bottom, for the bottom the value of aerial vector is in downward direction, electric field is in this direction. So what is the angle again? 90. So through this surface and this surface there is no contribution of flux. So the flux is contributed only through the curved surface area. So the surface integral of dA in this scenario will give you the curved surface area of a cylinder. And what is the curved surface area of a cylinder? It is 2 pi RH, which is going to be equal to lambda into h divided by epsilon naught, h and h, right? So from here E will be equal to lambda divided by 2 pi epsilon naught r. And this is going to be the value of electric field due to a linear charge distribution at a distance r. Right. As I told you, you can derive this thing using Coulomb's law also, but it would have taken at least some 10 to 12 steps. But here, look at the number of steps. We are able to do it faster, right? So one thing is, this is a value, right? Let me complete it, then you can copy. So for this value, we know that E is equal to lambda divided by 2 pi epsilon naught r. See, this is something you will not find in your textbook. If you plot the graph between electric field and distance. So tell me one thing, when I say the graph between electric field and distance, which one should I take on y-axis and which one on x-axis? Electric field on the y-axis and the distance on the x-axis. Why is it so? Because the x-axis is always independent. You're able to understand? Right. So lambda is a constant because uniform charge distribution. 2 pi epsilon naught is a constant. So E is inversely proportional to R. So it is of the form y is inversely proportional to x. So you will get a shape like this. So this is how the graph between electric field and the distance going to be for a linear charge distribution. Am I clear with this? Right? So please make a note of it. So there are two more applications. One is for an infinite plane sheet and the next one is for a uniformly charged spherical shell. First I'll finish this, then we can go to the next one. So now we'll find the electric field due to a uniformly charged spherical shell using Gauss law, right? So here, if you see, you have a spherical shell. Meaning of it is, it's a hollow sphere. And for a hollow sphere, remember, whatever charge you're trying to give to the system will not go and sit inside the sphere, rather it will sit on the surface. Why is it so? Because when I say hollow, there is no mass at all. Then there is no question of transfer of matter. Right? Right. So for this kind of a system, we'll find at 3 points. One is inside, one is outside, and the last one is on the surface. Okay, so if I take this to be the center, from the center first I am taking a point inside. If I take P1 to be inside, let's say at a distance small r. Okay, so at P1, and where is that point P1 considered to be? It is inside, right? Now, you tell me what is the kind of Gaussian surface that you are supposed to consider. So Gaussian surface should be symmetric with respect to the charge distribution. So where is the charge distributed? On the surface of the sphere. What is the symmetric shape to it? Another sphere, right? So if I take this to be the Gaussian surface, right? I've considered it through the point and everything. Here, one thing that I'm going to directly write is, I'll directly go to apply the Gauss law. So E vector dot dA vector is equal to 1 by epsilon naught times the charge enclosed by the Gaussian surface. Here, what is happening? Whatever charge you give is not sitting inside, it's sitting only on the surface. So what is the charge enclosed within? So charge enclosed is a 0. So when this is going to be 0, then the electric field will also be 0. Meaning there is no electric field present inside a spherical shell. So where does it start from? It starts only from the surface, because that is where the charge is present. Am I clear with this? Right. Now we'll do for outside point. For outside, I'll consider the point to be P2, for instance. Okay, what are the surface we can consider? With respect to the charge distribution, it's distributed on the surface. So I can consider another sphere which is concentric with respect to this. Right. Having said this, what is the next step? I need to consider an aerial vector. So what is going to be the aerial vector that I'll take? It will be dA, and it is directed in this way. And what is the direction of electric field? That is also in this way. So what is the angle between both? Angle between both is 0. So for point P2, that is outside, if I directly start applying the Gauss law, then I'll get the surface integral of E vector dot dA vector is equal to 1 by epsilon naught times 1 by epsilon naught times the charge enclosed by the Gaussian surface. This is where we need to be careful. If you take this whole concentric sphere, right, what is the total charge enclosed within it? It is going to be the charge that is present on the surface of the spherical shell, which is Q itself, right? So surface integral of E dot dA can be written as E into dA will be equal to Q enclosed is going to be equal to capital Q divided by epsilon naught. So what you can do is take the E outside, which implies E into the surface integral of dA is equal to Q divided by epsilon naught. So what is going to be the value of E? What is the surface integral of dA? Let's say this radius is R. 4 pi 4 pi R square will be equal to Q divided by epsilon naught. Point to be noted here is the small r is a variable. Okay. So what I'm trying to say here is, I'll take the radius of the sphere to be capital R, which is fixed. Whereas small r is a variable. At P1, P2, it keeps on varying. Right. So what will be the value of E? Q divided by, that's it. So this is the value of electric field at a point outside the spherical shell. If you see this outside the spherical shell, right, it is acting similar to a point charge. Meaning, for a spherical shell, if you calculate the electric field outside, it is the same as you having a point charge which is placed exactly at the center at a distance r from this point P2. Both are having same scenario. See, they both are not same, but it is acting as if it is a point charge which is placed at the center of the sphere. Am I clear with this? Now, the last one is on the surface, which is simple. So, when I say on the surface, no, what I'll do is small r will be equal to how much? Small r will be equal to capital R. So, small r is equal to capital R. Take this and substitute it there. What is going to be the value of electric field? E will be Q divided by 4 pi epsilon naught capital R square. Now understand this capital R square, capital R is a constant, small r is a variable. So is it clear till this step? Right, having said this, if I frame a small mathematical equation, meaning if I write the value of E, E will be equal to 0 when the value of small r is less than capital R. Meaning of it, if it is inside. Am I right? It is equal to Q divided by 4 pi epsilon naught. You can observe it to be capital R square when small r is equal to capital R. This is on the surface. Then what about this? Q divided by 4 pi epsilon naught small r square when the value of small r is greater than capital R, when it is going to be outside the surface. So having said this, when you plot a graph, right, between the electric field and R, this R is there, no, till the value capital R, it will be 0. It will be 0. After that, it will reach a value which is equal to how much? Q divided by 4 pi epsilon naught capital R square. After that, what will happen is it will decrease as a function of small r square. So this is the graph for Q divided by 4 pi epsilon naught small r square, and this is a very, very important graph. So I hope it is clear, right? So make a note of it.